The next segment we're going to build here under this register we just tested is the ALU, or Arithmetic Logic Unit. And I will base this unit on the famous 74LS181 4-bit ALU. This ALU is the ALU on a chip. It's very known from the past, from the late 70s, I guess. And it implements lots of mathematical and logic operations. And we're gonna be using it. I'll explain more about this ICs on the schematic part. For ALU, we also have its own register to store the output from the operations. And we also have a flags register to register whether we have any flags coming out from our ALU. For example, a carry flag or a zero flag or an overflow flag. And exactly for the overflow, the 74LS181 doesn't come with an overflow pin. It doesn't signal if the arithmetic it's calculating has overflown its capacity. So we're gonna build one overflow detector with one 74LS151, which is a multiplexer. We'll just use its combinational logic. It has inside many AND followed by a large OR gate, and we'll connect that in a way that will enable us to detect an overflow. I will also explain that more on the schematic. This is the schematics for our ALU based on the 74LS181. And it works by taking a number from the bus directly into the A inputs of the 74LS181, the A input, and the B input, it's coming directly from a register. I called it here also the B register for us to be easy to remember. And these are our two numbers that we'll be using in the operations inside the ALU. And the output from this operation comes to a register, also a 74LS377, so that we can store whatever we have as an output and then output it to the bus whenever it's convenient to us. And this interface here is also done with the 74LS245. Also some LEDs to visualize whatever we have stored in our register, and that's it for inputs and outputs. But we also have to deal with the controls for the 74LS181, and the 74LS181 needs roughly 6 control lines. From S0 to S3 we select the operation that will be done. This one I call logic F, logic function. It controls the 8th pin, that's a flag that will tell the 74LS181 if we are dealing with arithmetic or with a logic function. And we also need a carry input in case we had a carry from another operation that we wish to carry in, and also because we might have to set this if we're dealing with addition or subtraction with the 74LS181. And I'll show this right now on the data sheet. This is the table from the operations this ALU can perform. As I said, the S0 to S3, we select one from each of these 16 operations. The logic function is with this bit here set to either do arithmetic or logic, and the carry, we also have a table to differentiate. And we see a lot of different operations that seem rather random, but they're not. There is a reason behind this, and these functions here, these 16 functions, the logic functions, are here, and the arithmetic operations are the exact same 16 when we add a and the carry in case of this other column here. For example, this function here, f equals b, and if we add a and no carry, we get a plus b. And if you add the carry, then we have a plus b plus the carry. Another example is not b. A, if we add a plus not b plus carry, that's subtraction. That will be a minus b, and that's it here, a minus b. Because we know that a subtraction binary is just if we take this in choose complement, we just take the inverse of b plus 1. That's the choose complement, and add this to a, and we have then a minus b. We could test all of these functions, and we would successfully be able to prove that the arithmetic operations are just the logic operations when we add a plus the carry. And that's pretty interesting. And let me go back to our also worth mentioning, although we have all these operations, we probably won't be using not even half of them. We will of course be using a plus b and a minus b. We'll use a and b, a or b, a exclusive or b, but the rest I guess we won't be using not even the half of it. Let's see. Coming back here to the schematics, now that we know more or less what our chips will do, on the output we also have to deal with some flags in case we want to do some conditional jumps and other interesting things that we'll see when we get to the control logic, but we'll have to prepare for our flags. And one flag that's really easy to get is the carry output. Let's have a register to store whether we had a carry or not. And well, since this chip has an inverted carry output, I just added this simple transistor inverter here so that we'll store a flag when we have the carry and not the complement of that, not have the flag always active and not having the flag when we have the carry. I chose to do this because we just needed 3 components, small components, instead of a whole chip with other 6 inverters or the 5 inverters that we won't be using. So just a simple inverter with a transistor, and the output of that will store on 74LS183, a 4-bit register. And the other flag that we have here is the 0 flag. And the 0 flag is also easy to obtain, because the 74LS181 has this A equals B output on each of the chips, which will be high whenever A equals B. And not only this can signal us the 0 flag. For example, if we have if we store a 0 on the A input and A equals B, then we know that B is also 0. But we also can do other things. If we're counting, for example, and we store the number we have to count to in one register, when we get there, then A equals B, and we'll have this output high. And it's very interesting because on the datasheet we see that this output specifically is an open collector output. And this means, I have drawn this somewhere here, yeah. This means that we can have a wired AND gate with these outputs without having to use any logic gates. And this works the following. This transistor here is inside the chips, each of the 74LS181s. And what we get access to is the collector from each of these transistors from the A equals B output. And as we know, it is a logic high. That means if we connect a resistor to VCC and to this output, whenever A equals B, this output here will be 1 or 5 volts. And on all other cases, when A not equal B, well, we must have here 0. And that means that for almost all other situations, this transistor here will be conducting, so that we'll have a near ground reference here, just the drop of the transistor. That's actually a transistor inverter that we just saw for the carry output. And then inside the 74LS181 we have actually a not A equals B feeding this transistor here. So it will be conducting, always conducting, whenever A different B, so to say. And that's interesting because if we parallel both of the chips like that, we get an AND output for A equals B. Because for both chips, the only way that this output here will be high is if this and this are not conducting. Either one conducts and this output here is a 0. So it works pretty fine, and we save a chip for that. That's good. Good that the developers of the chip thought about this. But one thing that we do not have is the overflow flag. And the overflow flag can be important for us, because once that we'll be dealing with negative numbers encoded as choose complement, the carry bit is not always right, and the last bit might become corrupt in case we are dealing with some operation like minus 100 minus 50, and we should have minus 150, but we don't have enough bits for that, and so we get a positive number instead of a negative one. And we must be able to tell, or logic here must be able to tell whether this has happened, whether our last bit has become corrupt. And this is called the overflow flag. And I will demonstrate how we could get an overflow detector for this chip, because since we don't have one on it, and it works more or less like that. I'll get 2 examples here that we have to take care. The first one is, let's say the first word starts with the most significant bit is a 1, and the second word also a 1. Let's call this A word and B word. And the rest of the bits is a don't care. Let's put here a don't care. And in this situation, so let's suppose our output, or F, we get a 0 on the most significant bit, and whatever on the other ones. This is a situation that demonstrates an overflow if we're dealing with choose complement, because that's exactly what happened. We have a negative number here, a negative number here, and here's this actually should be a positive number, and that's impossible. So this is an overflow. We have to take care of this. And the other situation we could get is actually the opposite of this. If we have two positive numbers here, so the most significant bit will be a 0, and on our output, on F output, we get a 1 somehow. And for example, by adding here 100 to 50, we should get 150, but we won't, because the representation of 115 in choose complement is a negative number. So this last bit here is also corrupt, and we have to detect these two situations, and that's fairly straightforward. We could do this with some gates. For example, for this first situation here, we could get the last bit here, let's call it A7, and B7, and F7. And F7 here is the inverse of A7 and B7, so let's just invert it. Let's end this, and we get the function we're looking for. Well, whenever this here is a 1, it means an overflow. This is the first case. And the second case is could do more or less the same, but with the inverted out inputs. So A7, not A7, not B7, and F7. We end these three signals, and we have here our second case. And all we got to do now is OR them together. And we have here our overflow flag. Great. And this, we could build this. We would be successful on building this. But we would need AND gates, and we would need an OR gate. We would have to invert some inputs, and well, we would certainly need many chips to do this. And not only that, this is just the situation where we are adding A plus B. But if you're doing A minus B, we would have to have a different circuit. And as I mentioned, A minus B in choose complement is just A plus the inverse of B plus 1. So what the 74 less 181 is doing is exactly that. It's inverting B and adding the carry. And so to detect this, we would have also to replicate the same circuit here, inverting B. So we would have to take A7, not B7, and not F7, and end this together. And we would also have to get, this time, not A7, B7, it's the inverse of this, and F7. And end this together. And OR these two outputs to get then our other overflow flag, and we will have to then OR these two here together to get then a real flag here for all the possibilities. And well, you can see that this is already escalating a lot of chips just for a flag. Fortunately for us, there is a chip that will solve this problem pretty quickly, pretty neatly, and this chip is a multiplexer. It's the 74LS151 multiplexer, and as we can see on the datasheet, it consists on a OR gate at the end that connects to 8 4-input AND gates with an enable and 8 select lines and 3 and also 3 input lines here, or the inverse of that, 3 select lines and 8 input lines. Well, that's rather handy for us. For example, for the first A plus B, for the first AND gate that we had there, we had A7 and B7 and the not F7. And if you look closely, if we connect here to S0, we connect our A7 bit to S1 or B7 and to S2 or F7, then this I3 here, this gate here, does exactly what we want. We enable it here through I3. We say we are adding, so we are doing A plus B. So we take a bit from our control logic to tell that it's an addition, and we will then activate this AND gate here. The F7 comes not F7, that's exactly what we wanted, and A7 and B7, they are not inverted, so great, that's exactly what we needed. This is for I3, and I4 here is the rest of the circuit we needed for A plus B, which is not A7, not B7, and F7. So that's great. And the same analysis go to A minus B. We would have to activate then I1 and I6. If we do the analysis, it's connected on the way we need. And that's exactly what I've done here on the schematics. I wanted to show you all this before, so to be clear what was this multiplexer doing here. So it takes on its inputs the control lines S0 and S1, and S0, when S0 is high, it's doing an addition, and when S1 is high, it's doing a subtraction. We can easily check that on the data sheet of the 74LS181 quickly here, just for reference. When we are adding A plus B, S0 is high and S1 is low. When we are subtracting A minus B, S0 is low and S1 is high, so that's very convenient. We can use these lines then to control our multiplexer. Great. And the other inputs from the multiplexer are just connected to ground to avoid any false triggering. And then we added, then for S0 we got, as I said, here A7. It's the last bit coming from our second 74LS181. For S1, we got then B7 directly here from the register. And for S2, we got F7. Yes, from the 74LS181. And our output, finally, is our overflow flag. And it's being then stored on the flags register. And of course, not forgetting to mention, we also have a negative flag. That's just a flag connected to the F7 output. So whenever the last bit of our operation is set, we can, and we're dealing with choose complement, we know that's a negative number. Some LEDs for signaling, and that's it. That's, well, it was a rather long video, but I guess I covered it all. From this ALU we can start building it.